So what are we up today? So not last class, because we did, remember last class we did the absolute and relative coordinate system, but before that, we did a problem of two masses, two springs, which was, let's see if I can go back, it's going to be upside down. But basically, I don't know if you remember that figure that I gave you over here. For 2 degrees of freedom, you have x1 over the ratio of omegas, x2 over the ratio of omegas, no? Let's say you have two different masses. And here, what do we notice over here? This is the response in function of the frequency ratios. Is that we have one value where the response of x1 will be equal to what?
Would be 0.
0. So that, I think I told you at that time, so let's say we have this, okay? We have this one over here. So that will let us know, like for example, this is x1, this is x2. So we know at a certain x1, the deformation of this is 0, even though this is being excited, no? So we could use that fact as to try to play with the values of m, k, and m2 to try to find what would be the ideal value for those quantities, so that we could create some type of isolators, no, for this mass. Think about you have some type of machine that vibrates a lot, and you want to create a foundation that's going to remove the vibration. So it would be to find the right values so that your structure is not going to transfer the vibration into the base or vice versa. Okay? So we got that idea from that figure, so this is what we're doing today. Basically, so. So last page we have to scan this next. So 109. And you need this for the exam, so. So what's today, June 15?
Mm-hmm.
All right, so let's call this vibration isolators. All right, so let's take the simplest case. We have a mass here and 2 connected to a spring K2. M1, K1, and we're going to pick what's the name of this reference frame? Absolute or relative?
Relative.
This is the relative, okay? So we use the relative, which will have coupling in what? On the masses or the springs?
Of the springs.
Of the springs. And let's say this over here is subjected to a force vibration of V1 cosine capital omega t. Okay, so here what we're trying to do is to design what should be M2, K and M2, so that this will not vibrate anymore. Because this is the one which has the excitation, no? Mm-hmm. We could have put the force over here, doesn't matter, okay? The procedure will be identical. All right, so there we go. So what should be the procedure for this? First thing will be to find the equation of motion.
Mm-hmm.
So let's see how many masses we have. 2. So the first thing to do is some type of figure diagram. So let's see, this would be is that this way? I'm gonna okay. Maybe not. So let's do this for M1. Let's do this for M2. So let's see, what is M1 subjected to? What will be the forces due to K1? Assume this is moving up initially.
You K1, X1 down.
So K1, X1 down. Now what should be the one connecting this M1 to M2? Should be going
K2 times X2 minus X1.
K2, X2 minus X1. And let's not forget that this is the force M1, which is also subjected to the force F1 cosine omega t. And this will have what? A motion M1 x double dot 1, no?
Mm-hmm.
If we do the same thing for the mass 2, what are we going to have?
You're gonna have K2, X2 minus X1 going down.
So action reaction, K2, X2 minus X1 going down.
And I think that's it.
That's it. And here M2 x double dot 2. Okay, we could have done that one also using Lagrange, no? But just changing this. So now that we have this, we apply Newton's equation. I'm trying to do it on this page so I don't have to go to another page. So what will be the equation for M1? So measure of forces on the x direction, x1 direction will be equal to what?
M1, X1 and double dot.
So will be, yeah, but I'm trying to do the other way. So will be minus K1 X1, no?
Mm-hmm.
I do first the summation of forces, plus K2 X2 minus X1, plus F1 cosine omega t, equal to M1 X1 double dot. I was trying to squeeze everything, but probably I won't be able to do it. So this will give you what? M1 X double dot 1
Plus K1, X1.
plus
K1
K1
plus K2, X1.
Yeah, plus K1 plus K2 X1 minus
All right, minus K2, X2 equals F1 cosine
equal to F1 cosine
of omega t.
capital omega t. If we do exactly the same thing for the mass M2, we're going to have minus K2 X2 minus X1 will be equal to M2 X double dot 2, which will give us M2 X double dot 2 plus K2 X2, no, minus K2 X2, no, plus K2 X2 minus K2 X1 equal to 0. So we combine those two equations in matrix form. What do we get? No coupling with your mass matrix. Coupling on the stiffness, so first one K1 plus K2, minus K2, minus K2, K2. So I should leave a little bit more space here. And this should be equal to what?
F1 cosine of omega t and 0.
Correct. Okay, so over here we know that the total solution to that system will have two different parts, the homogeneous and the particular, no? Not really, because, yeah, we have the homogeneous and the particular. But we say that here we're just gonna do the particular solution, okay? So, just finding particular solution, which means what? That we're going to solve with the force, no? Instead of being 0.
Mm-hmm.
So in that case, what was the procedure? Remember?
Yep, first you assume that it's a solution of the same form with the same frequency as the forcing function.
Correct. So we assume harmonic solution. But this time we use the form of, so we'll have, if you want, x1 will be equal to x1 e I capital omega t.
But only the real part.
Yeah, we have to take only the real part afterwards, yeah. But just to jump, x2 will be x2 e I omega t, and the force let's say letter F1 would be equal to capital F1 real parts of AI omega t. And then, yeah, we have to take just the real part, okay? So if you want here real part, so we take the second derivative of this, we go and substitute into this equation, no? Okay?
Mm-hmm.
So what are we gonna get? Real part of EI capital omega t should be equal to what? Minus m1
Omega squared.
capital
plus-
omega squared plus
K1 plus K2.
k1 plus k2.
The next cell would just be minus K2.
This one would be minus k2,
Minus K2 again.
minus k2, and here we have
Minus M2 omega squared plus K2.
I'm running out of space again. And this should be equal to what? The real part of EI omega t of
F1 and 0.
F1 and 0. So now that we have that equation, what do?
Cancel out the exponential,
Cancel out the exponentials.
and then Don't you just set the top line and the bottom line equal to, or the top line equal to itself and the bottom line equal to itself?
I mean, let's see, let's write down the next line over here, or this was page 10. So basically, let me just do in detail once more. So we start with minus M1 capital omega plus K1 plus K2 minus K2 minus K2 minus M2 omega squared plus K2 x1 x2 equals to F10. So now we needed to solve for what?
Would it be, oh yeah, x1, x2.
X1, X2. So remember, I mean, we did this a bit, we use a different notation, but let's not use it, okay? What's, so X1, X2 will be equal to what?
The inverse matrix of
Yeah.
that thing times force.
Correct, so plus K1 plus K2 minus K2 minus 2 minus K2. So what did I do when we did this chapter? What notation did I use? I don't remember. Because it can get pretty messy here. Oh, pigeon. Okay, presentation. Did we use that notation with the z's or no? Oh yeah.
Yes, we did. I think so.
Okay. So when I go back to the class notes, we have here the problem of the force vibrations over here. So basically, this is the general equation. You have F1 and F2, no?
Mm-hmm.
Okay. So we assume the solution, the same thing we did now. This is the general form. And at the end, the equation we just wrote now is this one over here. But we change this notation with the Z1s. We ended up in, this is basically the equivalent, no?
Mm-hmm.
Yeah?
Yes, sir.
So maybe let's change the notation, and then the solution will be equal to this over here. Right, so it's that, so. So let's see. So let's just do it for the specific case. So let's say now defining Z11 as minus M1 capital omega squared plus K1 plus K2, Z12 minus K2, Z21 equals Z12 equal minus K2, and Z22 equal to minus M2 capital omega squared plus K2. So I'm just going to put here same procedure as in page 90. So if I use that notation, then the equation, this equation here becomes what? X1, X2 equals to 011, 012, 012, Z22. And I forgot something, I know this is the minus 1. So for 2 degree of freedom, so for matrix 2 by 2, we say that the inverse would be equal to what?
It was 1 over the determinant times the matrix revolves around itself, its axis.
Yeah, that's
Probably
a
not
good
the
way to put
technical
it.
term.
Yeah, I know exactly what you're saying. That's a good way to say it, actually. So it'll be 1 over,
The determinant,
which is Z11,
Z22
Z22,
minus Z12 squared.
Z12 square. And then here, we needed basically to switch this one, no? Basically it would be like almost rotating, yeah, rotating 90 degrees. So it would be, so Z11, Z22,
And then it was negative Z12 in the other two.
and then negative Z12, negative Z1, yeah. And here we have F1 and 0. So let's just do it for this case, okay? Since you might have to do this on the exam. So now from this equation, we can solve for x1, no? What will be x1?
So it would be F1 Z22
Okay, F1, Z22,
divided by that whole thing.
okay? And x2 would be equal to what?
Negative F1 Z12 over the whole denominator.
Okay, so all this ZZ here, they have me to write this down, but maybe let's go back to the other notation here now to see exactly what's happening. Are you done copying this page? All right, so now let's see what happens if we transform that back to the other notation. So this will give us, so x1 will be equal to f1 times z22, which is minus m2 omega squared plus k2 divided by, read that long term, it's not that important, but we need to write down, minus m1 omega squared plus k1 plus k2 times minus m2 omega squared plus k2. And x2 will be equal to minus f1 z12, which is minus k2, divided by the minus m1 capital omega plus k1 plus k2 minus m2 omega squared plus k2. Okay, so let's go back to the first page. In this case, we say that, what are we trying to do? We're trying to make
M1 stationary?
M1 stationary, so we want to make x1 equal to 0.
Mm-hmm.
Okay? So x1 equal to 0 means what? This needs to be equal to 0.
Yep.
So how can this be equal to 0?
If the numerator is equal to 0?
If this, so f1 is not equal to 0, so if this term over here is 0,
Yes.
then x1 will be 0, no?
Mm-hmm.
All right, so we can say this stuff. So x1 is equal to 0, so no deformation. Stationary, as you said. If minus m2 omega squared plus k2 equal to 0, which means m2 omega squared
Equals K2.
equals k2, but I'm going to simplify with this, or omega squared equal
K2 over M2.
k2 over m2, which really, what is this?
Kind of a natural frequency?
This is a natural frequency
Squared.
square, but for, let me just call it n2, no, for the block 2.
Okay.
Yeah?
Mm-hmm.
For block 2. So we can say that if the force frequency is equal to the frequency of the mass 2, I don't know what color to use. So what would be that would be the condition.
So resonance for block 2?
So, sorry?
Would that then initiate a resonance in block 2?
No. One will, no, you will see what happens, okay?
Okay.
So let's see what happens. So now, all right? Or this is correct, or let's say here, or omega equal to omega n2. Okay? or we can leave the omega square. So omega square equal omega n square equals K2 over M2. So this might get all this a bit more complicated, but let's see what would happen over here. So substituting, that result, which is omega squared equals K2 over M2 into X2, we'll see what happened with X2 now.
Mm-hmm.
Okay? What you were saying here. 110, 111. Okay, so we're going to substitute over here. I have no idea what's going to happen. I know what we should get, but I'm doing this calculation with you. So X2 will be equal to what? Minus F1, so F1 K2 I need your help here a little bit to minus M1 K2 M2 plus K1 plus K2 minus M2. Maybe I should have done the substitution with the other one, but K2 M2 plus K2. All right, so let's just look at this term over here, okay? So the denominator and let's just do the algebra with this one will be equal to what? M1, M2 K2 over M2 square, no?
Mm-hmm. That would be minus M2 K2 plus K1.
Yeah, let's do one by one. Minus, let's do now this one, minus
Okay.
M1,
Minus M1 K2.
minus M, but we have this M1 K2 over K. K2,
Alright, and then minus M2. I guess times, yeah, K2 over M2. Times K1 plus K2.
yeah. And then we have here plus, it doesn't get complicated, plus K2, K1 plus K2. Is it something we can simplify here?
Yeah, there's a bit.
So let's see. Not the first one.
First term would be M1 K2 squared over M2.
So let's see what happens. So M1,
It would be K2 squared divided by M2. Alright, and then the next one is minus M1 K2 squared over M2.
so we have again minus M1 over M2, K2 squared. So these two cancel out now.
Yep. Alright, and then you've got I guess it would be
minus
K1, K2.
So this m cancel out, so minus K2, no? Factor of K1 plus K2,
Mm-hmm. So,
and it's going to cancel with this one.
yep.
Okay, so that's probably going to cancel. So everything cancels out. Almost, no? So everything cancels out over here.
Yep, should all be 0.
Yeah, so you're right. So that means that it's going into resonance. Because if you divide something by 0, what does that mean?
Infinity.
It goes to infinity. So this cancels this one. Okay, so this is equal to 0. But I cannot go to 0. Cannot go to 0. Do we miss a term or something here?
I don't know.
Alright. M1, M2, K2 already to square. Minus M2, K2, K1 plus K2. Plus K2, K1 plus K2, no?
Maybe is it because there's no damping on this?
No, because if it goes to infinity, it's not a good thing. It should go to the static deflection. So we get M1 over M2.
The entire right term in the denominator cancels to 0. Because then 2's canceled, and then the K2's canceled.
Yeah, but we should have a K2 at the bottom staying. That's what I'm saying. Oh.
Should that be for x2 or for x1?
Or, no, X1 is going to be 0, no?
Yeah, it should be.
So
Right.
X2 it should be X2.
Strange.
Let's see, I'm looking at the algebra here, see if we miss something. Minus M1, M2, K2 squared. Minus K2, K1 plus K2. Plus K2 plus K1. So I use a different notation here on those notes, but I get that it's equal to the static deflection. That is interesting here because, all right, did we miss something before? No. Denominator Interesting. Right. I give you a figure. Do you have the figure that I gave you over here? The
Mhm.
page with the figure?
Yes.
Let's look at that figure and see what is that one saying. Yeah, so basically, yeah, it's saying that it needs to go to the resonance. The ecstatic at omega yeah, so when capital omega equal omega, no, so will be our omega. Omega sub A will be the omega of the absorber. The response goes to infinity when there is no damping. No?
Mm-hmm.
So that makes sense? What can we do? So this means that when capital omega equal omega and 2, which is the, we have that the limit of x2 will be infinity, no?
Mm-hmm.
So basically on that figure over here, this capital omega, this is the omega n2 for us. So what is the assumption we did for the second one? What do? We replace the omega, oops, what is it? We replace the omega by the omega n2, no?
Mm-hmm.
Which corresponds to which point?
And it's omega over omega n equals 1.
So, which is this point over here, no?
Yep.
So what happened at this point?
Goes to infinity.
This goes to infinity, but this is, yeah. So basically what happened is this. Oh, we put on the figure. So it is observed from the figure that we had our 2 degrees of freedom. Where is that figure? We had our 2 degrees of freedom, this one over here. Oops. Yeah?
Mm-hmm.
So we have omega 1, omega 2, that we could say, we can see over here, this will be omega 1, this will be omega 2.
Mm-hmm.
Okay? We transform all that system into what? If x1 becomes 0, it becomes like we transform everything into one system at this ratio where the x2 will be in resonance.
Mm-hmm.
That's all I can say, no?
Yeah, pretty much.
But which is funny because when I follow here the notation, so I need to check my class notes. I'll show you if you want. You see, I didn't do it, but oops. You could rewrite all these responses supposedly under the form of the ratio omega over omega so m2, which is the omega of the absorber. I ended up with this expression at the bottom. So when I was doing this is to equivalent to what we call the omega n equal to 1, but when substituting to the x2, it was giving the static deflection and not 0. So I need to check this, okay?
All right.
But actually what we got is what is being shown on the figure, no?
Looks like it.
Because we are here, we count this value and we find that that we are the resonance.
Mhm.
But for this point, what would be the deformation of x1?
0.
x1 is 0, no? Yeah?
Yes, sir.
So, all right, we got the theory. Let's organize the pages here a little bit. So, 110, 111, 109. Team. So exercise. Okay, this is 113. For example,
Excuse me, we can't see.
let's start. So the problem says all right, so I read the problem statement and I do the model. So a diesel engine weighing 3,000 Newton is supported on a pedestal mount. It has been observed that the engine induces vibration into the surrounding area through its pedestal mount at an operating speed of 6,000 RPM. Determine the parameters M2 and K2 of the vibration absorber that will reduce the vibration when mounted on the pedestal. So basically, we assume the pedestal to be M1 over here. So we know M1 is how much? Is the weight, so it's weight 1 would be 3,000 newtons. So the pedestal it vibrates at 6,000 RPM. We're going to assume this is the force here, F1 cosine omega t. So if you want all this over here is our modeling for the foundation.
Okay.
Okay? And basically now they say determine the parameters M2 and K2. So we're going to attach to this an absorber of mass M2, K2. So you want this will be the absorber. All right, of that system. So we need to determine, the answer is to determine M2 and K2 of the vibration absorber that will reduce the vibration when mounted on the pedestal. The magnitude of the exciting force, so F1, is 250 Newton, and the amplitude of the motion of the absorber mass is limited to 2 millimeters. So what does that mean?
That means x2 would equal that number.
Will be equal to 2 millimeters, okay. So 0.02. All right? Okay. So this is our model. So we're not going to derive the equation again, no? This is exactly the same problem. So let's use the results that we obtained. So I cannot use any of those class notes here. All right, so first thing we need to do is maybe transform those 6,000 RPM in radians per second. So how can we do that?
Divide by 60 and multiply by 2 pi?
Yeah, one revolution will be 2 pi radians, no?
Mm-hmm.
And 1 minute will be 60 seconds. So from here, we'll get that the capital omega is, I think I have it over here, 628.3 radians per second. Okay, I don't know why in this problem they gave us the weight to be 3,000 newtons. So what does that mean about the mass?
It's that divided by g?
Yeah, so it's so how much would that be?
Approximately 300. Give you an exact value in just a moment.
Would be 300 something, you know, 300.
Yeah, something like that.
I don't know how much. You have to do a calculation because I don't have them. So
Okay. All right, it's 305.81.
with the new result that we got, I don't really see how we can do this one, but we have to figure it out.
Well, maybe since we're not limiting the motion to 0, maybe this time it won't resonate.
Yeah, but it was the denominator that was equal to 0, not the x2.
True, but that's only because it was at the natural frequency, which probably only happens when you have x1 equal to 0 or x2 equals to 0.
Yeah, but here we want x1 to be equal to 0, no?
Oh, I thought we wanted,
Or
okay.
is x2, I don't know. and the amplitude of motion of the absorber mass is to be limited to 2 millimeters.
Mhm.
So x1 is still equal to 0.
Oh, okay.
So we have a problem.
Maybe should we throw a damper on there then?
Yeah, a damper will not change much of the result, but it will not let this go to. All right, so we got it here, so. I mean, theoretically, the result, I want to tell you what I mean. Look at this figure, okay?
Mhm.
Conceptually, what should happen is that this system of N2 and K2 needs to generate a force which will be of the same amplitude of F1,
Mhm.
but on the opposite direction. Or if you want, 180 degree out of phase, no?
Yeah.
Of this one,
Mhm.
okay? So that's really what should happen, so. So could we do it that way? Yeah, okay, so I'm gonna get the same answer that we should get, but it's not gonna be. All right, so now we can say this, so. All right, so for x1 equal to 0, the system N2 of the system N2K2, which is the absorber, must generate a force of same amplitude
And same frequency and completely out of phase?
yeah, same amplitude of F1, no?
Mhm.
But out of phase, or with 180 degree out of phase. So that, what does that mean? We know that F1 should be equal to K x2, no?
Mhm.
So from this equation, we could say that K2 will be equal to F1 divided by x2 which numerically is what? So K2 will be equal to F1, which is 250, and X2 we say was 2 millimeters, no?
Mhm.
So K2 will be equal to F1 over x2 equals to 250 divided by 0.002.
Mhm. And it's 125,000.
125,000.
Mhm.
Okay, and what is the other condition that we know for x1 equal to 0? This will occur at what frequency?
Omega n2.
When this is equal to the frequency of the absorber, no?
Yep.
Which in our case will be square root of k2 over m2.
Mhm.
All right? So with this, we know what is the frequency. We can find that, let's see, omega squared equal k2 over m2, or m2 be equal to k2 divided by the
Omega squared.
capital omega squared. So we do a numerical application. M2 is equal to 125 10 to the 3. And omega we found to be 628.3 square. Which gives you what for the mass?
0.317 kilograms if you round.
0.317.
Yep.
Oh, I zoom, sorry. It's because I zoom in, so that's why you cannot see now everything. Sorry about that. Okay? But I still need to go and check my original class notes, not the one we did today, okay? But the ones on my photo because I had a little issue with the x2. I don't know if it is because of just this equation of motion, because the other one I have it is completely general.
Mhm.
So I need to go and check something. So what time is it? About 4:15?
Yep.
Okay. So if you want, any question about this? I mean, let's look at if this makes sense or not, because more than, trusting the big complicated math, let's go back again to this part. What is the function of this? It needs to create a force that would be opposite to this one, no?
Yes.
Okay? So that it could cancel it out. So that's the whole idea. So you know that a spring can create a force equal to kx, no?
Mhm.
But obviously you have a mass. So the mass under k also induce that you need to have a certain frequency. So obviously you need to create the same force. Let's see if that makes sense. You need to be able to create the same force at what frequency?
At that frequency.
At the same frequency, no? Would be the easiest thing. So if the frequency of this system is equal to the frequency of the exciting force, now the thing you need to do is to find out what is the value of k for a certain value of x that will generate the same opposite force.
Mhm.
Does that make sense or no?
Absolutely.
because we did all the mathematical equations, but you could just solve it by thinking about the problem, no? All right? So that's it. Let's look at the exam. Well, I need to upload, I think, a file. The one on the eigenvectors, I think I forgot to upload it yesterday into Canvas. Other bunch of files here I need to upload again. So let me do that first. Videos, I think I'm good now. So EP, I think this one, I wanted to do it before, I couldn't find it, so I hope it's in this computer. I hate when this stuff changes from my office or file. Upload a new file that I cannot see obviously. And I'm going to get there, choose file. Desktop.
I can probably.
That's right. Open. I shall update some upload here. All right. Save. Okay, so let's go to the announcements, no, to assignments. Here I call it exam 2. Oh, you didn't see it because I didn't publish it. That's probably why, no? It should have helped.
Yeah, probably.
So I made it due on the 26th, but at 11 a.m., okay?
Okay.
So I didn't give you too much because I don't want to spend too much time. But basically what I did, I'm going to be honest with you, I kind of went to books and I looked at some problems, but I did not give you the same ones. I modified them, you know?
All right.
So I tried to spice them a little bit. So basically in this one, what do you have? You have one mass over here,
And
the mass of the bar, another mass over here, a spring, no? So basically this is lying in that direction, this is lying in that direction, this is the bar. Find the equation of motion using Newton's equation and Lagrange.
Okay.
Okay? And obviously whatever distance this is going to move, this is going to move. So you can just use 1x, no? So the equation of motion, write them down in function of x and the angle of theta. Did I put this stuff? No. Okay. Can't do that. This one, something similar. Okay? You probably can find something similar in the textbook, but I modified, okay, a little bit. So you have this one, and I put some data here. The whole idea is that you solve the eigenvalue problem. That you first need to find the equation of motions, then you solve the undamped problem for the eigenvalue eigenvector problems. Then I give a force to F1 and F2, and I want you to solve this, do the hand calculation, but also do the numerical solution with the MATLAB code.
Okay.
Okay? And 3, basically here I try to complicate this, but this is the same thing. This is a system with a damper. And what I ask you, so this will be your M1, this will be your M2, no? Yeah? I put a spring at the top and the bottom, if you want. And I ask you to determine what is the mass of this one so that this X is 0.
Okay.
Okay, so find M so that this becomes a damper. So really, once you have the equation of motion, it will be identical to what we have been doing. I'm just trying to make this a little bit more complicated, no? This is our foundation. This is our damper, no? Okay? That if you want will be connected at the top and the bottom. And that's all.
Okay.
But again, remember, you need to show me that you understand the material. So make sure that you explain everything to me, like if I was your little brother, okay?
All right.
All right, doesn't need to be a lot, and I'm not that concerned about the final results, okay? I'm gonna say that you show me that you understand the material, that you know how to use the tools that you have learned in this class.
All right.
Okay? I'm not looking that you tell me at the end of the exact result. I don't even have it myself, okay? That's why I completely made up those problems.
All right.
Okay? So again, try to make everything is clear, well presented, neatness. Everything is neat, well presented. Because one thing, the way you present it is the way I think it's in your head. Okay?
Okay.
So make sure everything is clear. Alright, and you can upload any what happened? You can upload any PDF or MATLAB file, but if you're gonna do that, yeah, just put all the exam in one PDF file, and then if you want to give me your MATLAB file, you can give them to me. I might not look at them, okay? But if you want them, you can do those things. Okay? And if you have any question, you can ask me, okay? If you start working on a problem and you think something is missing, just come and ask me and I'm gonna let you know.
Alright.
But I kind of thought about each one of them. I think you should have everything.
All right.
So that will be it for today. So next week I'm not planning on doing a lot more because you're already working on the exam. So I might give you a little introduction about acoustics, but depending on how I do it, you might like it or hate it.
All right.
You know, if I just go to the very apply, like what is acoustic? You define noise, how you create noise, random noise. But if I go what is acoustic, you need to solve the differential equation for the wave equation for different boundary conditions and so on. You're not gonna like it because it's pure math, no? We'll see.
All right.
All right, so have a good weekend.
Thanks. You too, Professor. What happened to the other guy?